if you looked at the programming languages of today, you probably get this idea that the world is object-oriented. But it's not. It's actually parallel. You've got everything from the lowest level, like multi-core machines, and up through networking and so on and so on. But it gets all the way up to users, who knows, planets, the universe. There's all these things that are happening simultaneously in the world. And yet the computing tools that we have are really not very good at expressing that kind of worldview. And that seems like a failing. But we can fix that if we understand what concurrency is and how to use it. Now, I'll assume that most of you at least heard of the Go programming language, which is what I've been working on at Google the last few years. And Go is a concurrent language, which means that it has some things in it that make concurrency useful. Like it's got the ability to execute things concurrently, the ability to communicate between things that are executing concurrently, and it's got this thing called a select statement, which is a multi-way concurrent control switch. If that doesn't make any sense to you yet, don't worry. But when we announced Go, which was about 2 years ago, all these programmers out there said, oh, concurrent tools. I know what to do. I can run stuff in parallel. Yay. But that actually isn't true. Concurrency and parallelism are not the same thing. It's a commonly misunderstood problem, and I'm here to try to explain why and to show you that concurrency is actually better. What would happen to these people who were confused was they'd take a program, they'd run it on more processors, and it would get slower. And they think, this is broken, it doesn't work, I'm going away. But what was really broken was their worldview, and I hope I can fix that. So what is concurrency? Well, concurrency, as I'm using it and as it's intended to be used in the computer science world, is a way to build things. It's a composition of independently executing things, typically functions, but they don't have to be. And we usually express those as these interacting processes. And by process, I don't mean a Linux process. I mean the sort of general concept that embodies threads and coroutines and processes, the whole thing. So think in the most abstract possible sense. So it's the composition of independently executing processes. Parallelism, on the other hand, is the simultaneous execution of multiple things, possibly related, possibly not. And if you think about it in sort of a general hand-wavy way, concurrency is about dealing with a lot of things at once. And parallelism is about doing a lot of things at once. And those are obviously related, but they're actually separate ideas. And there's a little confusing to try to think about them if you don't have the right toolkit. So one is really about structure, concurrency, and one is about execution, parallelism. And I'll show you why those are important. So concurrency is a way to structure a thing so that you can maybe use parallelism to do a better job. But parallelism is not the goal of concurrency. Concurrency's goal is a good structure. So here's an analogy you might be familiar with. If you're running an operating system, it might have a mouse driver, a keyboard driver, display driver, network drivers, whatever else. And those are all managed by the operating system as independent things inside the kernel. But those are concurrent things. They aren't necessarily parallel. If you only have one processor, only one of them is ever running at a time. And so there's a concurrent model for these I/O devices, but it's not inherently parallel. It doesn't need to be parallel. Whereas a parallel thing might be something like a vector dot product, which you can break down into microscopic operations that you can execute on some fancy computer in parallel. Very different idea, not the same thing at all. So in order to make concurrency work, though, you have to add this idea of communication, which I'm not going to focus on too much today, but you'll see a little bit about it. So concurrency gives you a way to structure a program into independent pieces, but then you have to coordinate those pieces. And to make that work, you need some form of communication. And Tony Hoare in 1978 wrote a paper called Communicating Sequential Processes, which is truly one of the greatest papers in computer science. And if you haven't read it, if anything out of this talk sinks in, it's that you should go home and read that paper. It's absolutely amazing. But based on that, a lot of people with lesser minds have followed and built tools to use his ideas into concurrent languages, like Erlang is another one that's great. Go has some of these ideas in it. But the key points are all in that original paper, with a couple of minor exceptions, which I'll come up to. But look, this is all way too abstract. We need gophers. So let's get some gophers going. Here's a real problem we want to solve, okay? We have a pile of ancient, obsolete manuals, say the C++ 98 manuals, now that C++ 11 is out. Or maybe it's the C++ 11 books and we don't need them anymore, whatever. The point is we got to get rid of them. They're taking up space. So we have a gopher whose job is to take the books from one pile and move them into the incinerator and get rid of them, okay? But with only one gopher, it's going to take a long time if it's a big pile. And also, gophers aren't very good at moving books, although we've given them a cart. So let's put another gopher in the problem. Except he's not going to get any better, right? Because he needs the tools. And this is kind of pointless. We need to give him all the parts he needs in order to do this. So this gopher needs not only the ability to be a gopher, but he also needs the tools to get the job done. So let's give him another cart. Now that's going to go faster. We're definitely going to be able to move books quicker with 2 gophers pushing the carts. But of course there may be a little problem because we're going to have to synchronize them. They can get stuck at the incinerator or the book pile, getting each other's way, running back and forth. So they're going to need to coordinate a little bit. So you can imagine the gophers sending each other little Tony Hoare messages saying, here I am, I need space to put the books in the incinerator, or whatever it is. But you get the idea. This is silly, but I want to make it really clear. These ideas are not deep. They're just good. Okay, well, how do we make them go faster? Well, we double everything. We put 2 gophers in, and we double the piles and the incinerators as well as the gophers, and now we can move twice as many books in the same amount of time. That's parallel, right? But think of it instead of parallel as really the concurrent composition of 2 gopher procedures moving books. So concurrency is how we've expressed the problem. This gopher guy can do this, and we parallelize it by instantiating more instances of this gopher procedure. And that's called the concurrent composition of processes, or in this case, gophers. Now, this design is not automatically parallel. Because, sure, there's 2 gophers, but who says they both have to work at the same time? I could say that only 1 gopher is allowed to move at once, which would be like having a single core computer. And the design is still concurrent and correct and nice, but it's not intrinsically parallel unless I can make both those gophers move at once. That's when the parallelism comes in. Having 2 things executing simultaneously, not just having 2 things. Okay? That's a really important model. But once we've decided that we understand we can break the problem down into these concurrent pieces, we can come up with other models. So here's a different design. Okay? Now we've got 3 gophers in the picture. It's the same pile of books, the same incinerator, but now we've got 3 gophers. Right? There's a gopher whose job is just to load the cart. There's a gopher whose job is just to carry the cart and then presumably return the empty back again. And then there's a gopher whose job is to load the incinerator. So 3 gophers, it's going to go faster. It might not go much faster though, because they're going to get blocked. You know, the cart with the books is going to be in the wrong place, and there's time to bring the gopher running back with the empty where nothing useful is getting done with the cart. So let's clean that up by having another gopher return the empties. Okay? Now, this is obviously silly, right? But I want to point something fairly profound that's going on here. This version of the problem will actually execute better than this problem, this guy, even though we're actually doing more work by having another gopher running back and forth in here. So once we've got this concurrency idea, we're able to add gophers to the picture and actually do more work, but make it run faster, because the concurrent composition of better managed pieces can actually run faster. And it's pretty unlikely that things will work out just perfectly. But you could imagine that if all the gophers were timed just right and the piles were just right and they knew how many books to move at a time, this thing could actually keep all 4 gophers busy at once. And it could, in fact, move 4 times faster than our original version. Unlikely, but I want you to understand that it's possible. So here's an observation that's really important, and it's kind of subtle. We improve the performance of this program by adding a concurrent procedure to an existing design. We actually added more things, but the whole thing got faster. And if you think about it, that's kind of weird. It's also kind of not weird because you added another gopher, and gophers do work. But if you forget the fact that he's a gopher and think of it as just adding design, adding things to the design can actually make it more efficient. And that parallelism can come from better concurrent expression of the problem. It's a fairly deep insight that doesn't look like it because there are gophers involved, but that's okay. So we have 4 concurrent procedures running here, right? There's a gopher that loads things into the cart. There's a gopher that takes the cart and trucks it across towards the incinerator. There's another gopher who's unloading the cart's contents into the incinerator. And there's a 4th gopher who's returning the empty carts back. And you can think of these as independent procedures, just running as independent things completely. And we just compose those in parallel to construct the entire program solution. But that's not the only way we could do it. Here's a completely different design. Sorry, not completely different. Here's the same design made more parallel by putting another pile of books, another incinerator, and 4 more gophers. But you see, the key point is here, we're taking the idea that we have, how we break the problem up, and once we understand its concurrent decomposition, we can actually parallelize it on different axes and get better throughput, or not, but at least we understand the problem in a much more fine-grained way. We have control over the pieces. In this case, if we get everything just right, we've got 8 gophers working hard for us, burning up those C++ manuals. Or maybe there's no parallelization at all. Who says that all these gophers have to be busy at once? I might only be able to run one gopher at a time, in which case this design would only run at the rate of a single gopher like the original problem, and the other 7 would all be idle while he's running. But the design is still correct. And that's a pretty big deal, because it means that we don't have to worry about parallelism when we're doing concurrency. If we get the concurrency right, the parallelism is actually a free variable that we can decide just how many gophers are busy. Or we could do a completely different design for the whole thing. Let's forget the old pattern, put in a new pattern, and we'll have 2 gophers in the story. But instead of having one gopher carry it all the way from the pile to the incinerator, we put a staging dump in the middle. So the first gopher carries the books to the dump, drops them off, runs back, gets more. The second guy sits there waiting for books to arrive to the pile, takes them from there, and moves to the incinerator. And if you get this right, you've got 2 gopher procedures running, but they're kind of different procedures. They're kind of the same, but they're subtly different. They have slightly different parameters. But if you get this system running right, at least once it's started, it can, in fact, in principle, run twice as fast as the original, even though it's a completely different design in some sense, the original one. But of course, once we've got this composition, we can go another way. We can parallelize the usual way. Run 2 versions of this whole program at once and double again. Now we've got 4 gophers, maybe up to 4 times the throughput. Or we could take a different way again and put the staging pile in the middle into the original concurrent multi-gopher problem. So now we've got 8 gophers on the fly and books getting burned at a horrific rate. But that's still not good enough, because we can parallelize on another dimension and go full on. So here's 16 gophers moving those books to the burning pile. And obviously this is very, very simplistic and silly, but it's got gophers in it, so that makes it good. But I want you to understand that conceptually, this is really how you think about running things in parallel. You don't think about by running in parallel, you think about how you break the problem down into independent components that you can separate and understand and get right, and then compose to solve the whole problem together. So, what does this all mean? Well, first of all, there are many ways you could do this. I showed you just a couple. If you sit there with a sketchbook, you can probably come up with 50 more ways to have gophers move books. There's lots of different designs. They're not necessarily all equivalent, but they can all be made to work. And you can then take those concurrent designs and refactor them, rearrange them, scale them in different dimensions to get different abilities to process the problem. And it's nice because however you do this, the correctness of your algorithm for doing this is easy. It's not going to break. I mean, they're just gophers, but the design is intrinsically safe because you've done it that way. However, this is obviously a stupid problem. This has no bearing on real work. Well, actually it does. Because if you take this problem and you change the book pile into some web content, you change the gophers into CPUs, you change the cart to the networking or the marshalling code or whatever it is you need to run to move the data, and then the incinerator is the web proxy or browser, whoever you want to think about the consumer of the data, you've just constructed the design for a web serving architecture. And you probably don't think of your web serving architecture as looking like that, but the fact is it's pretty much what it is, right? And you can see by substituting the pieces, this is exactly the kind of designs that you think about. And when you talk about things like proxies and forwarding agents and buffers and all that kind of stuff, scaling up, more instances, they're on this drawing. You just don't think of them that way. So they're not intrinsically hard things to understand. If gophers can do it, so can we, right? So let me now show you how to use these ideas a little bit in building things with Go. Now, I'm not going to teach you Go in this talk. I hope some of you know it already. I hope lots of you go and learn about more about it afterwards. But I'm going to try to teach you a little tiny bit of Go, and then hope the rest kind of gets absorbed as we do it. So Go has these things called Go routines, which you can think of as being a little bit like threads, but they're actually different. And rather than go into the details of how they're different, let's just say what they are. So let's say we have a function that, in this case, takes 2 arguments. If we call that function in our program, then we wait for the function to complete before the next statement executes. That's very, very familiar. You all know that. But if instead you put the keyword Go before you call that function, then what happens is that function starts running, but you get to run right away, at least conceptually. Not necessarily. Remember concurrency versus parallel. But conceptually, your program keeps running while F is off here doing his thing, right? And you don't have to wait for the F to return. And if that seems confusing, just think of it as being a lot like the ampersand in the shell. So this is like running F ampersand off in the background. Okay? Now, what exactly is a Go routine? Well, they're kind of like threads, right? Because they run together. They're in the same address space. Within a program they are, at least. But they're much, much cheaper. It's pretty easy to make them, and they're very cheap to create. And then they get multiplexed dynamically onto operating system threads as required, so you don't have to worry about scheduling and blocking and so on. The system takes care of that for you. And when a Go routine does need to block, like doing a read system call or something like that, no other Go routine needs to wait for it. They're all scheduled dynamically. So they feel like threads, but they're a much, much lighter weight version of them. And it's not an original idea. Other languages and systems have done things like this, but we gave them our own name to make it clear what they are, so we call them Go routines. Okay, now I mentioned we have to communicate between these things, right? So to do that, we have these things in Go called channels, which are like a little bit like pipes in the shell, but they have types and they have other nice properties, which we're not going to go into here today. But here's a fairly trivial example. We create a timer channel and say it's a channel of time.time values. And then we launch this function in the background that sleeps for a certain amount of time, delta t, and then sends on the timer channel the time at that instant, time.now. And then the other process, because the other Go routine, because this one was launched with a Go statement, doesn't have to wait. It can do whatever it wants. And when it's ready to hear that the other guy is completed, he says, I want to receive from the timer channel whatever that value is. And that Go routine will block until there's a value to be delivered. And once it is completed, that will get set to the time at which the other Go routine completed. Trivial example, but everything you need is in that one little slide. And then the last piece is a thing called select. And what it does is it lets you control your program's behavior by by looking at multiple channels at once and seeing who's ready to communicate. And you can decide to rate, in this case, between channel 1 or channel 2, and the program will behave differently depending on whether channel 1 or channel 2 is ready. In this case, if neither is ready, the default clause will run, which lets you sort of fall through if nobody's ready to communicate. If the default clause is not present in the select, then you'll wait until one or the other of the channels is ready. And if they're both ready, the system will just pick one randomly. So this will come up a little later, but it's pretty much like a switch statement, but for communications. And if you know Dijkstra's guarded commands, it should seem fairly familiar. Now, I said Go supports concurrency, and I mean it. It really supports concurrency. It is routine in a Go program to create thousands of Go routines. And we were once debugging, actually live at a conference, a Go thing that was running in production that had created 1.3 million Go routines and had something on the neighborhood of 10,000 actually active at the time we were debugging it. And to make this work, of course, they have to be much, much cheaper than threads, and that's kind of the point. So they're not free. There's allocation involved, but not much, and they grow and shrink as needed, and they're sort of well managed. But they're very, very cheap, and you can think about them as being as cheap as Gophers. You also need closures. I showed you a closure sort of under the covers before. Here's just proof that you have them in the language, because they're very handy in concurrent expressions of things to create nonce procedures. So you can create a function that here, in this case, composes a couple more functions, returns a function. It's just to show that it works, and they're real closures in Go. So let's use these elements to build some examples, and I hope you'll learn a little bit of concurrent Go programming by osmosis, which is the best way to learn. So let's start by launching a daemon. You can use a closure here to wrap some background operation you want done, but not wait for it. So in this case, we have two channels, input and output. And for whatever reason, we have to deliver input to output, but we don't want to wait until the copying is done. So we say go func for a closure, and then have a for loop that just reads the input values and writes them to the output. And the for range clause in Go will drain the channel. So it'll run until the channel is empty and then exit. So this little burst of code just drains the channel automatically and does it in the background, so you don't have to wait for it. And it's a little bit of boilerplate there, but it's not too bad, and you get used to it. Let me now show you a very simple load balancer, a very simple one. And if there's time, which I'm not sure there will be, I'll show you another one. But this is a simple one. So imagine you have a bunch of jobs that need to get done, and we've abstracted them away here, or maybe concretized them into a work structure with 3 integer values that you need to do some operation on. So the worker tasks, what they're going to do is compute something based on these values, and then I've put a sleep in there so that we're guaranteed that we have to think about blocking, because this worker task may block an arbitrary amount of time. And the way we structure it is we have the worker task read the input channel to get work to do, and have an output channel to deliver the results. So those are the arguments to this function. And then in the loop, we range over the input values, doing the calculation, sleeping for some essentially arbitrary time, and then delivering the output to the output to the guy who's waiting. So we have to worry about blocking. So that's got to be pretty hard, right? Well, there's the whole solution. And the reason this is so easy is that the channels and the way they work along with the other elements of the language let you express these concurrent things and compose them really well. What this does is creates two channels, an input channel and an output channel, which are the things connected to the worker. They're all reading off one input channel and delivering to one output channel. And then you just start up some arbitrary number of workers. Notice the go clause in the middle there. All these guys are running concurrently, maybe in parallel. And then you start another job up that says generate lots of work for these guys to do. And then you hang around in this function called receive lots of results, which will read the values coming out of the output channel in the order that they complete. And because of the way this thing is structured, whether you're running on one processor or 1,000, the job will run correctly and completely and will use the resources well. It's all taken care of for you. And if you think about this problem, it's pretty trivial, but it's actually fairly hard to write concisely in most languages without concurrency. Concurrency makes it pretty compact to do this kind of thing. And more important, it's implicitly parallel, although you don't have to think about parallelism if you don't want to. But it also can scale really well. There's no synchronization or nonsense in there. Num workers could be a huge number, and the thing would still work efficiently. And the tools of concurrency, therefore, make it easy to build these kind of solutions to fairly big problems. Also notice there was no locking, no mutexes. All these things that people think about when they think about the old concurrency models, they're just not there. You don't see them. And yet, this is a correct, concurrent, and parallelizable algorithm with no locking in it. That's got to be good, right? But that was too easy. So let's see how we're doing. Yeah, I got time to do the harder one. This is a little trickier, but it's the same basic idea, but done much more realistically. So imagine we have a load balancer that we want to write that's got a bunch of requesters generating actual work, okay? And we have a bunch of worker tasks, and we want to distribute all these requesters' workload onto an arbitrary number of workers and make it all sort of load balance out so the work gets assigned to the least lightly loaded worker. So you can think of the workers may have large amounts of work they're doing at once. It's not just one at a time. They may be doing lots. And there's lots of requests going on, so it's a very busy system. This could be maybe on one machine, which is how I'm going to show it to you. But you could also imagine that some of these lines represent network connections that are doing proper load balancing. Architecturally, the design is still going to be safe the way we do it. So what a request looks like is very different now. We have some arbitrary function, closure if you like, that represents the calculation that we want to do. And we have a channel on which we're going to return the result. Now notice the channel is part of the request. In Go, unlike a lot of the other languages like Erlang, the channel idea is there, and it's a first-class value in the language. And that allows you to pass channels around, and they're kind of like file descriptors in the sense that if you have the channel, you can communicate with someone, but anyone who does not have the channel is not able to. So it's like being able to pass a phone call to somebody else to do, or to pass a file descriptor over a file descriptor. It's a pretty powerful idea. So the idea is you're going to send a request with a calculation to do and a channel on which to return the result once it's done. So here's an artificial but somewhat illustrative version of the requester. What we do is we have a channel of requests that are coming in, and we're going to generate stuff to do on that work channel. So we make a channel which is going to go inside each request to come back to us for the answer. We do some work, which I've just represented here as sleeping. Who knows what it's actually doing. And then you send on the work channel a request object with the function you want to calculate and whatever that is, I don't care, and a channel on which to send the answer back. And then you wait on that channel to get the result to come back. And once you've got that, you probably have to do something with the result. So this is just something generating work at some arbitrary rate. It's just cranking out results. But it's doing it by communicating on channels with inputs and outputs. And then the worker, which is on the other side of this picture. Remember, we've got requesters. We've got requesters delivering data to the balancer, which is the last thing I'm going to show you, and workers on the right. And what the workers have in them is a channel of incoming requests, and then a count of pending tasks, which is going to represent the load that worker has, the number of tasks he's actually got busy. And then an index, which is part of the heap architecture, which I'll show you in a second. So then what the worker does is receive work from his requester, his request channel, which is part of the worker object. Call the function on the worker side. So you pass a request, I guess from your point of view, pass the actual function from the requester through the balancer into the worker. He does the answer, and then he returns the answer back on the channel. Now, notice that unlike a lot of other load balancing architectures, the channels from the worker back to the requester do not go through the load balancer. Once the requester and the worker are connected, the balancer's out of the picture, and the worker and the requester are talking directly. And that's because you can pass channels around inside the system as it's running. Okay? And then, if you want to, you could also put a go routine inside, put a go statement inside here and just run all these requests in parallel on the worker. It would work just fine if you did that, but that's enough going on at once already. Okay, and then the balancer is kind of magical. You need a pool of workers, and you need some balancer object you're going to put the balancer's methods on. And that includes a pool, and then a single done channel, which is how the workers tell the balancer that they've finished their most recent calculation. So then the balancer is pretty easy. What it does is it just forever does a select statement, waiting either for more work to do from a requester, in which case it dispatches that request to the most lightly loaded worker, or a worker tells him he's done, in which case you update the data structure by saying the balancer, that worker has completed his task. So it's just a simple two-way select. And then we just have to implement these two functions. And to do that, what we actually do is construct a heap. I'll skip that bit. It's not very exciting. You get the idea. Dispatch, all dispatch has to do is grab the least loaded worker, which is a standard priority queue implementation on a heap. So you pull the most lightly loaded worker off the heap. You send it the task by writing the request to its request channel. Now you increment the load because it's got one more guy you know about, and that's going to influence the loading distribution. And then you push it back onto the same spot on the heap and go, and that's it. You've just dispatched it, and you've updated the data structure, and that's what, 4 executable lines of code. And then the completion task, which is when the worker's finished, you've got to do the sort of inverse. There's one fewer guy on this worker's queue, so you decrement his pending count. You pop him from the heap, and you put him back on the heap, and that'll put him back where he belongs in the priority queue. And that's a complete implementation of a semi-realistic load balancer. But the key point here is that the data structures are using channels and go routines to construct this concurrent thing. And the result is scalable, it's correct, it's very simple, it's got no explicit locking, and yet the architecture just sort of makes it all happen. And concurrency is therefore enabled parallelism intrinsic in this thing. And you can actually run this program. This program is all compilable and runnable. And it works, and it does the load balancing, and the things all stay at exactly uniform load, modular load quantization. It's pretty good. And you can, of course, have, I never said how many workers there are or how many requesters there are. There could be 1 of each and 10 of the other, or 1,000 of each, or 1,000,000 of each. The scaling still works, and it still behaves efficiently. One more example, which is somewhat more surprising, but it fits on a single slide, so it's a nice one to finish. Imagine you had a replicated database. So you've got a database with the same data in each of multiple, what we call shards at Google, same instance, right? And what you want to do is deliver a request to all of the databases and a query and get back the result, but they're all going to be the same. You're using this to go faster by picking the first guy to answer, first guy to come back with the answer is the one you want. So if one of them's down or disconnected or something, you don't care because somebody else will come in. So here's how to do that. This is the full implementation of it. You have some array of connections and some query you want to execute. You create a channel which is buffered to the number of elements, the number of replicants inside this, replicas inside the query database. And then you just run over all of the connections to the databases, and for each one of them, you start a go routine up to deliver the query to that channel, to that database, and then get the answer back by this do query call, and then deliver the answer to the single channel that's holding the result for all of these guys. And then after you've launched them all, you just wait on the bottom line there, and wait for the first guy that comes back on that channel is the answer you want. You return it, and you're done. And the thing is, this looks like a toy, and it kind of is, but it's actually a complete correct implementation. The one thing that's missing is clean teardown. You want to sort of tell the servers that haven't come back yet when you've got an answer that you don't need them anymore. And you can do that. It's more code, but not an unreasonable amount more. But then it wouldn't fit on a slide. So I just want to show you that this is a fairly sophisticated problem to write in a lot of systems. But here it just sort of falls naturally out of the architecture because you've got the tools of concurrency to represent a fairly large distributed complex problem. And it works out really nicely. So, 5 seconds left. That's good. Conclusion. Concurrency is powerful, but it's not parallelism, but it enables parallelism, and it makes parallelism easy. And if you get that, then I've done my job. So if you want to read more, there's a bunch of links here. There's Golang.org has everything about Go you want to know. There's a nice history paper that Russ put together that's linked there. I gave a talk a few years ago that led up to us actually doing Go, which you might find interesting. Bob Harper at CMU has a really nice blog posting called Parallelism is Not Concurrency, which is very similar to the idea that concurrency is not parallelism, but not quite. And then there's a couple other things. The most surprising thing on this is the concurrent power series work that Doug McElroy, my old boss at Bell Labs, did, which is an amazing, amazing paper. But also, if you want a completely different spin on it, the last link on the slide is to another language called Sawzall, which I did at Google shortly after coming there from Bell Labs. And it's remarkable because it is incredibly parallel language, but it has absolutely no concurrency. And by now, I think you might understand that that's possible. So thanks very much for listening, and thanks to Hiroko for inviting me, and I guess it's time to have some drinks or something.